we're going to put everything together now. Now we're going to solve inequalities that are not quadratic-based equalities. With quadratic-based equalities, we can use our knowledge of the parabola being open up or open down. But when you don't have quadratic-based equalities, it's a little more complicated. With polynomials, we want to try to get the factored form, and if we can't get the factored form, then it's really challenging. Because if we want to compare the results, we want to compare the results to 0. That way, if it's greater than 0, we're just looking to see when positives occur. And if it's less than 0, we're just looking to see when negatives occur. So if we don't have a factored form, then we got to solve a polynomial with compared to 0, which means we got to find the x-intercepts. And that's not easy to do when you don't have factored form. Okay, so again, we're not going to have that issue. I'm just pointing that out. Now, when you have a rational function, you kind of got to know when it's above and when it's below the x-axis when we compare to 0. If you have a rational form that's not compared to 0, then we got to change it to compare it to 0. Okay, so just a statement of the 3 types of problems. So all we're doing for class today, I'm going to give you 3 examples. I'm going to have you do 3 on your own, then we'll go over it. And then I just summarize the steps of solving rational inequalities. Okay, so this is all we're doing today. All right, well, the first one's something we're kind of familiar with. We've already looked at factored forms, and we've already did test points on a number line with factored forms. And we did that to make graphs. In this case, we're not worried about the graph. We just want to solve what is the interval of the domain, or intervals, plural, where this is true. Now, you can do this by making the graph. The solution to this problem for the example is when it's greater than 0. Where's the graph above the x-axis? So that is plausible. Okay, so we have our first example, then I'll do the second example, the third example, and then your turn, and then that's basically it for the day. Okay, so the fact that this is in factored form, really helpful because we can quickly get the x-intercepts and then just start using test points. And we have an even multiplicity, but we don't really need to know that because we're just solving an inequality. Okay, so let's see, you put these equal to 0, this one's going to be 1, this one's going to be -4/3, this one's going to be 3, and this one's going to be 5. Okay, and I'm not going to try to do this spatially correct. I just want to make sure there's enough room. All right, so 5, I'll put a dot here, -4/3, 1, and 3. Now again, if you're more comfortable making the graph, you can do that. Nothing wrong with that method. Whereas the graph above the x-axis is essentially the solution. Right, but I'm just going to use test points. Tends to be quicker. All right, so there's regions of the interval. And any number in this interval is either going to cause the y's to be negative, which means the graph is down here, or the y's to be positive, which means the graph is up here. Okay, so we want to use a number in each interval to see what happens. Is it positive or negative? And that's the idea. All right, so it doesn't really matter which number you pick. So just pick something nice that works for you. So I'm going to use -3 here. And then if you can use a 0 or a 1, that tends to be the best choice. All right, so those are my test points. I'm going to put them in here and see what we get. Now notice this one's always positive. So this third binomial here is always going to wind up being positive. It's the other 3 that are going to change their signs. Okay, again, that's another way to think big picture. Okay, so over here, -6, negative, negative, always positive, negative. Okay, -3. -3, see, that's negative, negative, always positive, and now that x plus 5 becomes positive. All right, now 0. 0 minus 1, negative. This is going to become positive. That's always positive. And 0 plus 5 is positive. Okay, now the 2. 2 minus 1, positive. Put 2 in here, positive. This is always positive. 2 plus 5, positive. Okay, and then this is a 4. You can see that doesn't really look like a 4. All right, so now 4. 4 minus 1, positive. This is positive when you, that's always positive, and then 4 plus 5, positive. Again, because you don't have to calculate the value, this is quicker. That's why we want to compare this to 0. All right, now what are we looking for? We're looking for when we have a positive y. All right, 3 negatives, nope. 2 negatives, oh, so right here. A negative, 3 positives, nope. 4 positives, okay, so right here. And also on the other side of 3. And notice that happened when we had the even multiplicity. So on either side of the 3, there's going to be no sign change. Now look at how many domains we have. In between negative 4 over 3 and negative 5. Okay, now this is a little tricky because we can't equal 3. If that had a line under it, then we could just say greater than or equal to 1. So if we had a line under the symbol, then it could equal 3. And so then greater than or equal to 1 would be okay. But we don't have a line under it. So we're going to have to write 2 separate statements here. All right, so I'm just going to put the word or. Greater than 1, less than 3, or greater than 3.